Today we're going to take a qualitative look at transmission, reflection, and refraction. Let's take a look at what happens when we send a wave pulse in on a string. In this case it's a string with beads on it. And you notice here that the last bead is held in the C-clamp, so it's held fixed. So let's see what happens. There's the pulse coming in. I'll pause it right here, but you can see because the green bead is being held, from going upwards, there's going to be a reactionary force pulling that red bead downwards, and all the red beads should end up coming downwards. They all get pulled down, and then the pulse is going to go back on the other side, like so. So we get this inversion, 180-degree phase change, when we've got a fixed end. If we change this to a loose end, so now this last bead is free to move up and down vertically, and we send in our pulse, you can see that the green bead now goes upwards. It's actually going to go up twice as high as the original pulse. But this time the pulse doesn't get inverted. It comes back on the same side. There's no phase change. So when we send a pulse into a fixed barrier, we get an inversion. But when we send a pulse into a free end, we do not get an inversion.
Let's do a quick question. Pause the video, try the question, come back for the answer. First thing to notice is that we've got a fixed end. So it's fixed right here. That means it's got to come back on the other side. The other thing that you want to notice is the short side here. This is the long side. This is the short side. The short side is leading. When it reflects, the short side is still going to have to lead. So your answer has to look like B here, where you've got the inversion and you've got the short side leading.
We can take this a little bit farther and imagine a pulse that's sent in from a light medium and then goes into a heavier medium. So we might imagine here a coil spring with very thin wire coils. That would be the light medium, and then a spring with heavy wire coils would be the heavier medium. So this is the incident pulse coming in here. This here would be the transmitted pulse, and this one coming back here would be the reflected pulse. So you want to notice here the reflected pulse does get inverted. And that should make sense to us because the heavier spring is going to have more inertia. And that's going to prevent the lighter spring from moving at the junction there. So it's going to be more like a fixed end. All because of inertia. So some of the energy continues forward, some of the energy gets reflected back. So let's consider what happens when we have an incident pulse in a heavy spring and it's going into a lighter spring this time. So here's our transmitted pulse, and you'll notice here the reflected pulse is actually coming back on the same side. So there's no inversion this time, and so this lighter spring is kind of like a free barrier, which kind of makes sense because the heavier spring is going to kind of do what it wants with the lighter spring. So the lighter spring is like a free barrier. And notice here that the incident pulse, it actually gets bigger in the lighter spring, even though we know some of the energy is going back as a reflected pulse. So this doesn't violate the law of conservation of energy because it takes a bigger pulse in a lighter spring to have the same energy as a smaller pulse in a heavier spring. However, in general, you get a greater fraction of the energy of the pulse being transmitted when you go from heavy to light, and a smaller fraction being reflected when you go from heavy to light as compared to light to heavy. So these waves on strings and slinkies and springs, those are considered one-dimensional waves. Water waves are considered two-dimensional waves, and we use a particular type of diagram to represent these waves. So if over here those are the water waves, then we can draw a line right along the crest of a wave, and that would be what we call a wave front. So this here is a wave front. And of course, waves will move in a direction that is perpendicular to that wavefront. So this here would be called the wave ray, and it just denotes the direction that the wave is moving in. So we might have a diagram like this to represent this situation here. And something that's worth noting here is from the universal wave equation, V equals F times lambda, we know that the frequency is determined by the source. So the frequency of all these waves is the same. And that means that the speed is going to be proportional to the wavelength. So if we see a shorter wavelength here and a longer wavelength here, then that means that these waves are moving faster and these ones are moving slower. This type of diagram here can be used to represent sound waves as well, even though sound waves are three-dimensional. And all we'd really be doing there is looking at a two-dimensional cross-section, a two-dimensional plane of the three-dimensional sound waves in order to form a representation that we can put on paper quite easily.
Okay, so let's take these two-dimensional drawings a little farther. Right now we've got a diagram here of some water waves, and on one side this might be some deep water. This would be some fast-moving waves over on this side, and on the other side some shallower water where the waves move more slowly. So once again we have a ray coming in perpendicular to the wave fronts. This would be called the incident ray. Some of that wave would reflect off the boundary, and it would go off in about that direction, and of course there would be the wave fronts. I'm not going to draw them all, but there would be wave fronts perpendicular to that ray. This would be called the reflected ray. And then we'd have to define a line here. It's called the normal, and we can have it on both sides here. It's a line that's perpendicular to the boundary between the media. And you draw it wherever the incident ray comes in and hits the boundary. Then we can draw a normal at that point. But that allows us to define a couple angles. First angle that we're going to define is called the angle of incidence. I'm going to use an I for the angle of incidence. But you always measure the angle I from the normal to the ray, never from the boundary to the ray. It's always from the normal. On the other side, I'll call this R prime. That'll be the angle of reflection. So that I can write, this is actually the law of reflection. Let me write it over here. The law of reflection. It simply says that whatever that angle I is, it's going to be exactly the same as the angle R primed. In other words, the angle of incidence must equal the angle of reflection. Now we can also draw a refracted ray or transmitted ray. It of course is going to be perpendicular to these wave fronts on the other side. And that allows us to define another angle. I'll call it R. That would be the angle of refraction. And once again, it's measured from the normal to the ray. This is the refracted ray, or the transmitted ray if you prefer. Of course, it's going to be perpendicular to all of those wave fronts in that medium.
So summarizing those key features of the refraction diagram, we have an angle of incidence and an incident ray, angle of reflection, reflected ray, angle of refraction and a refracted ray. And we're going, in this case, from a fast medium to a slow medium. And we know that because the wavelength here is longer than the wavelength here. And also take note here that the wavefront at that transition between the two media is a continuous wavefront. And if you've got a continuous wavefront and a longer wavelength here and a shorter wavelength here, then the only way that that'll be consistent is if you have a change in direction of the ray towards the normal.
We're just saying how when light travels from a fast medium, say air, into a slow medium, say glass, that the incident ray, it does not continue on its straight line path, it bends towards the normal. Now, in the case of light, there's a very nice way to explain that, a very nice analogy at least. Light, it always takes the least time to get from point A to point B. Now, we can kind of make a comparison between light and a lifeguard trying to save a person in distress. Because they can move a lot faster on the sand when they're running compared to the water when they're swimming, they should take a path somewhat like this so that they're covering more of the distance on the sand, a greater percentage of the total distance on the sand. And if that's the case, then of course they're bending towards the normal. Now, in a general case, even when it's not light, you can use this axis analogy to remember which way the light's going to bend. Once again, we're going from a fast medium where the axis will roll very quickly on the sidewalk into a slow medium, which is the grass. Now, if that's the case, this wheel here, it's going to hit first. And this wheel here is going to continue at a higher speed. And that's going to cause some rotation of the axis, and the axis will, once again, bend towards that normal line.
So to summarize, if you're going from a fast medium to a slow medium, and suppose this is the normal, this is the incident ray, then instead of going in a straight line, it's going to bend towards the normal. It's getting closer to the normal. But when you're going from slow to fast, of course everything is the opposite. So this time, instead of going in a straight line, you're going to get farther away from the normal, which means you're getting closer to the boundary. So slow to fast is away from the normal.
Let's do a quick question. Pause the video, try the question, come back for the answer. So the second medium here is the fast medium. The first medium is the slow medium. So two things have to happen. One thing is that the wave ray has to get farther away from the normal. So this one or this one both get farther away from the normal. And the second thing that has to happen is that because the speed is proportional to the wavelength, we want to go to a longer wavelength from a shorter wavelength. So this one here is wrong, and the correct answer is B.
In the particular case where you're going from a slow to a fast medium, so this is only for slow to fast. So here's our slow medium, here's our fast medium. Then, of course, if we sent in an incident ray, it would bend away from the normal, something like that. If we increase our angle of incidence, there's going to be a particular angle of incidence which we call the critical angle. So when the angle of incidence is equal to this critical angle, the refracted ray bends so far that it tries to run along the boundary. we're saying here that the angle of refraction is equal to 90 degrees. And that's when light tries to run along the boundary. But it turns out that's not possible. So none of the light gets transmitted. And what happens is all of the light is reflected. So if the angle of incidence is greater than or equal to that critical angle, we get total internal reflection. No light is transmitted from that slow medium into the fast medium. It all gets reflected and stays in the slow medium. The reason that fiber optic cables are able to transport light signals is because of total internal reflection. So if this is a fiber optic cable and you send in a light signal, that light signal will undergo total internal reflection each time it hits the side of the fiber optic cable. So there's no transmission outside of the cable. No energy is lost. So the fiber optic cables are made of materials that have a high optical density, and that means that there will be a large critical angle. So this angle of incidence here, and here, and here, and here is always going to be less than that critical angle for this high density material. And so there'd be absolutely no transmission outside of the cable. In the summertime, when you're driving in a car, you might have had a situation where you saw a puddle in the distance on the highway, but as your car got closer, the puddle disappeared. And that's due to refraction in the critical angle. And it's because the air close to the pavement is very hot, and light travels faster in hot air than it does in the cooler air above. So say we have a cloud up here, and light from the cloud comes down. It's entering this hotter air, so you get some refraction away from the normal. And we get this gradual bending as it gets hotter and faster, hotter and faster. And eventually, you're going to reach the critical angle. And that light is going to reflect back. So the light is going to stay within that cooler air. And of course, you're going to get a little more refraction as the light leaves the hot air and enters the cool air. This time, of course, you'd have some bending towards the normal. The brain here, it interprets any light that comes into it as having come in a straight line. So it sees the light from the cloud back here somewhere. And then there's all these shimmering effects because the light travels into this hot air where there's convection currents occurring. In fact, the idea of a desert mirage is due to this as well. Usually when we think of a desert mirage, we think somebody's just got wishful thinking. They wished that there was some water that they'd be able to drink. It's not a mental illusion, it's an optical illusion. So once again, it can be a cloud here. Light from the cloud enters the eye through that path. Eye and the brain interpret that light as having come in a straight line. So the light from that cloud seems to be seen here underneath the ground. And once again, because of the shimmering, it gives the appearance of having some water there. Here's a little experiment you can try the next time you're in a swimming pool and have some goggles. Go under the water, hold your breath, wait long enough for the surface to get calm, and then look up. And you'll find that if you look through an angle here of about 98 degrees, that you'll see the entire panorama of 180 degrees above the water's surface. So for instance, if some light's coming from this toe here, it would go into the slow medium, the water, from the fast medium, and it would bend towards the normal along this path here. So that toe would show up at about 98 degrees. Now, if you go beyond that cone, you get total internal reflection. So if there's a fish over here, that might be seen by total internal reflection. The light from the fish would totally internally reflect and come back to the eyes. So within the cone of 98 degrees, you'd see the panorama above. But if you look outside that cone, you're going to see reflections from things in the water that are next to you. Let's summarize the big ideas from the video. First idea was that if you sent a pulse into a fixed barrier, then the pulse would come back on the other side. It would be inverted. So you get inversion at fixed barrier, but not at free barrier. Second idea was if you went from a heavy springs to light springs, then if you go from light to heavy, you get an inversion on reflection. The reflected pulse is inverted. And we also mentioned that we get more transmission and less reflection if you're going from heavy to light. And finally, we looked at these two-dimensional wave drawings, and we drew things like normals and incident rays and reflected rays and transmitted or refracted rays. We drew wave fronts, and the wave fronts were closer together if you're in a slower medium and farther apart if you're in a fast medium. We called this angle the angle of incidence, this angle was the angle of reflection, and this angle here was the angle of refraction. And we saw that the angle of incidence has to be equal to the angle of reflection. We also saw that if the angle of incidence is greater or equal to the critical angle, in the case that you're going from slow to fast, then you get total internal reflection. And then the total internal reflection was used to help explain fiber optic cables, as well as desert mirages, and those highway puddles that we see sometimes. So please take the time to like videos, to make comments, to ask questions, become a subscriber, sign up for notifications, become a member or a Patreon.
And that's all for today, folks. Thank you very much.